Old technology has always really interested me, whether it's an old car, rocket, radio, electronics, anything like that, and I always want to find out how it works and why it was designed that way. Included in that list is my grandfather's car battery charger from roughly the 1950s, 1960s. I wanted to add a voltage and current meter in series with it so that I could hook it up to a battery and see how well it was charging, what voltage I was at without the need to go find my voltmeter, put it in line with it, and it's just a couple extra steps that I didn't feel like doing. So anyway, some of the stuff that I found inside was really fascinating in terms of how they created the different voltage signals, how the power supply behaved without a battery on it versus just a load like a resistor. So coupled with my old battery charger, I also have a very old oscilloscope that I took a look at some of the signals coming off of it, and I thought you guys might appreciate some of this older tech in some of the troubleshooting aspect of what I was doing. So just wanted to bring you guys along for the ride. Maybe you'll learn something and appreciate some of this older tech. So let's get to it. So like I said, this was my grandfather's battery charger, battery tender, whatever you wanted to call it, from back in roughly the 50s or 60s, and I'll show you why I've been roughly able to estimate what date it came from. On the outside, you've got a 3-rocker switch for charge, off, and then trickle charge. Now, when it's trickle charging, some of the voltage and current goes through this incandescent light bulb right here. You might have seen in the intro, this light bulb was lit up a little bit, and as more current is going into the battery, so you have a very dead battery, this light bulb goes from brighter down to a little bit dimmer. And that's been extremely helpful in terms of maintaining the battery life and health without dumping so much current into it. The voltmeter and ammeter that I added is right there in the middle, and then the original ammeter that it came with is over here. Now when I say original, I mean original to me. I have no idea if this is the actual original one. I don't think it is because it's been riveted into place, and on the inside it looks like it was a little bit of a hack job, so I'm not sure if the original one broke. I assume it probably would have sat flush into the frame, and then my grandfather just wanted another ammeter, so he threw it in there. So from the outside it's a little bit rough, but I didn't want to fix up any of the paint or any of the aesthetics of it. I think it's really cool the way that it looks, and some of that charm of having some of the paint chipping I think is really, really cool. So now what I'm going to do is I'm going to turn it sideways and open it so that you guys can see inside and see what I was dealing with in terms of the electronics. Alright, so before we get started, just to point out, anything that is brightly colored, like these red wires, blue wires, this capacitor, anything down in here is not original. I just added that for the voltmeter and the current meter. That being said, some of the older tech that I found inside of here, like I mentioned before, really fascinated me and I wanted to learn a little bit more about it. One thing in particular, you can see back here these 2 squares with these prongs hanging out of it. That is what's called a selenium rectifier. And those were created in about the 1930s and they lasted through the mid-60s, which is why I'm dating this at roughly the mid to late 50s, early 60s. That's also based on what my father has told me. Now, I have never seen a selenium rectifier in basically anything. Everything that I own is probably 80s and later, so that's when, you know, transistors, silicon rectifiers, those things have been in place. Everything got a lot smaller, everything got a lot more energy efficient, so this was very, very foreign to me. I had to ask my father, who's an electrical engineer, what the heck even is this? Where am I tapping into power? How is this all going to work? Because I fully expected to open this thing up and just find a transformer with a 6-volt and a 12-volt output. I would tap into somewhere along those lines and then I'd be good to go. Come to find out, this box uses the selenium rectifiers. It doesn't produce a perfectly clean DC signal, which we'll show here in a minute on the oscilloscope, and that's why I needed to enlist his help into finding out what was going on. From what I can tell, it almost looks like whenever they had this open last, they just spray painted literally everything in brown spray paint. The transformer is covered in what looks like brown paint. The inside of the case, you can see where it used to be black and they spray painted it brown. So at some point this was black and then brown and then I think black again, or brown and then black again, I'm not entirely sure. Looking on the inside, like I said before, the 3-prong switch for figuring out the trickle charge on and off. The switch on the bottom, I forgot to mention it. The switch is a 6-volt or 12-volt switch. And then here on the right, you have the back end of the original ammeter. And then now back in there, you can, let me see if I can zoom in. Back in here, you can now see my my ammeter and voltmeter hooked into there. So I'm going to zoom back out here. Additionally, on the back, in this area, right by the Selenium Rectifiers, is this circuit breaker. I believe it operates on temperature, so when it gets too hot, it kind of disconnects the circuit and then shuts itself down. That way, if it says, oh my God, I've been dumping 10 amps of current through this battery for an hour, I'm starting to get way too hot, maybe something is wrong. This is kind of like that primitive version of a circuit breaker. So I can't find any model numbers on anything inside this thing. So when I was sending pictures back and forth with my father, it was pretty much him saying, well, I've seen this before, so I think this is what's going on. And I've seen this before, so I think I know what's going on here. Looking at the power that comes in through the wall, you've got 120 volts AC. One leg of it goes to the transformer and the other leg goes through that rocker switch, whether it determines which winding it's going into in the transformer. So one leg goes into the 12 volt section, one leg goes into the 6 volt section. There's a center tap which comes out the back. I know it's really hard to see. This is kind of a rat's nest, but it goes to one side of the ammeter. The other side goes up here to this rocker switch if it's on and off. So depending on which switch this selector on the bottom is hooked up to, goes into the different winding on the back of the transformer, and then the other switch comes up to the form of charging selector switch. So when I was talking to my father to say, hey, how are we going to fit this voltmeter in here? Where am I going to get power from? He looked at this and basically said, you're going to have a dirty signal, and the way that this ammeter works is it taps into the ground side of your current. So you need to break that line. Don't break the positive side. You need to break the ground side, and then that will accurately show you how much current is going through the system. Now, in addition to needing to break the ground side for the current sensing part of the ammeter, the ground for the power also has to be tied to the same exact place. Otherwise, you'll get some voltage irregularities. I'm not sure about the technical term, but basically you'll start having higher voltage versus lower voltage, and you could cross paths, and then that's never good. So it would have probably fried the device. The device itself is cheap, but I really wanted to minimize the potential damage that I could do to this system just because of how old it is and how cool I think it is. So I checked everything twice to make sure everything was hooked up properly, so that when I turned it on that first time, there were no issues. So like I said, needed to break the ground side, which goes out the clips to the back. In order to check how much current was flowing out, needed to get power from the one output from the transformer, have it go through a capacitor, and that capacitor just filters the signal and holds it at a steady voltage instead of having it, sine wave up and down all over the place. It especially helps when there is not a load on the system. It holds at a constant value. That way the display on the front shows a constant value instead of up, down, up, down. Back here in the switch is also where the light bulb is wired in, and it's just wired up to one of the legs, so it just diverts power around that way. When working on this, I had to be especially careful on where live voltage was and what was grounded and what wasn't. I almost was taking my probes from like a foot away to try and make sure I wasn't touching anything, just because this is quite old, and I knew that there was a good chance that I could shock myself if I wasn't paying attention. So after I got it all buttoned up, everything seemed to be working okay, but there were a couple additional tests that I wanted to run to see what kind of voltage ripple I was getting, how clean the signal was, and make sure that the voltage that I was reading on the display was the actual voltage that I was seeing. Hence the need for the oscilloscope. So I'm going to button this up a little bit and switch back over to the oscilloscope so we can talk about that and why we used it. So before I turn this on, a quick explanation. I've actually taken the back off of the charger, disconnected the capacitor, as well as rerouted the power around the voltage display. I'll explain why here in a second. So coming back over here to the oscilloscope now, I'm going to turn this on and I have it monitoring the output of the charger with no load attached. Once this warms up here a couple seconds, there we go. We're going to go ahead and we're going to see this signal on the display. Now give me just a second, I'm going to shut the lights off. And before I shut the lights off so that it's a little bit easier to see, you see this ripple that's occurring near the top of the sine wave? You'll notice when I shut the lights off that that ripple goes away. That's because the charger and the lights are plugged in to the same outlet, so that's some interference you can see going on. Now let me just readjust here to get a clearer look at the oscilloscope. Okay, so as you can see, this is a very clean sine wave, but when looking at the peak-to-peak voltage change, each one of these vertical divisions is 5 volts. That's about a 0, 5, 10, maybe 15 volt swing in the output, and that was causing the voltmeter to really not be happy when showing the display. You would see it fluctuate between 18 and 3 and all over the place, and even though one would think this is oscillating so fast that it shouldn't make a difference, for the cheap voltmeter that I had put in, it was just not happy at all. So this is why we added the capacitor in the circuit. So if I come here and I hook up the capacitor to this guy, what you should see is we should see at this peak of every wave just a flat line going across. So as you can see there, once I hook it up, now I don't have any of that oscillation and I have a much cleaner signal going into that voltmeter. So if I remove it, I've got my dirty signal. If I add it, much cleaner, happier signal. Now, I don't know if this is the fault of the Selenium Rectifiers or if this is just a fault of old technology from the 50s, but this is why now in power supplies there's tons of capacitors to filter the signal and give you a much cleaner voltage output. So I'm in trickle charge mode right now, and no capacitor, no voltmeter, bypassing all of that, so this is how it originally was made. When I hook up roughly a 1 amp load via a 10 amp or a 10 ohm resistor rather, you'll notice at the base of each of my waves, I no longer have the bottom half of that sine wave. I have this sharp point, and that's creating some unhappiness in the signal going throughout the circuit. Additionally, if you look over here, you'll see that that light bulb has turned on for the trickle mode. I'll come back here. So I'm going to go ahead and change this now from a resistive load. I'll actually hook it up to the battery and we'll see how the signal changes there. So now I'm on a battery instead of a resistive load, and you can see the battery acts as a gigantic capacitor, so there's no issue with the charger holding a steady voltage across, and you can see that because this is just a flat line across the entire thing. Now, why I wanted to throw the test in there with the resistive load is, say I wanted to run something that runs on 12 volts and doesn't have a capacitor or a battery built into it, this would help filter that signal and make it a lot cleaner, as well as not messing up the voltage and current display going on. So these tests that I just showed was without the capacitor and the other components inside. Now I'm going to reset up the box over here so that it does have that capacitor and it does have the voltage meter displayed. Okay, so now I've got voltmeter is reset back up. So as you can see, I'm sitting here idle at 18.7. That's partially in thanks to the Selenium Rectifiers and how root mean squared and all that works, as well as the capacitor thrown in there. We'll come back over here to the oscilloscope, and you'll notice sitting here idle, I no longer have that sinusoidal wave on the output voltage. Now, if I take this and I hook up my resistive load, you'll notice I'm back to having those pointed valleys on my wave. However, it's a little less significant, and you'll notice on the voltmeter I have a much more stable voltage reading here. So my peak-to-peak voltage is not as varying. And then I'll come back here. I'm going to hook this up to the battery instead of to this resistor. That way we can see, number one, that the current meter on the display is working, but also with a battery load, again, we have a very flat line for voltage. And looking back over here, I'm now charging this battery happily at 13.3 volts and about half an amp. It might be a little bit hard to see, but the light bulb is on when I'm in the trickle charge mode. And as we switch from trickle to normal charge, you'll notice not only did the light bulb go out, but my current increases. So I've gone from about 400 mils to about 800 mils. And this will change as the battery gets charged. The voltage and the current values will change a little bit, but the trickle charge is very handy for just keeping the battery topped off, and it's cool to see the light bulb in action. One additional function that I found out, since the way that I had wired this up in back powering the voltmeter from a couple of the leads, is even if I unplug this guy and then switch it to the on position, it's now a voltmeter for the battery. So I thought that was really cool and might help in some of my troubleshooting ventures. So anyway, that's all I have to say about this old battery charger. I think it was really cool taking a look inside and seeing the stuff like the Selenium Rectifier, the old circuit breaker, the ancient transformer that I'm surprised is even still working, and then playing around with the new voltage display. I'm very satisfied that it accurately reports out the voltage and current going to the battery. And it was also really cool to bust out the old oscilloscope to take a look at some of the signals coming out of the voltage coming from the battery charger. And it is extremely satisfying to see when switching from a static load like a resistor that my battery voltage is correct, the current going to it is correct, my little light bulb is still working, and I have a very stable voltage output. I hope you guys enjoyed this video. I really like taking a look at some of this older tech and incorporating some of the old tech that I have into the troubleshooting aspect of it. If you did enjoy it, consider subscribing, watching some of my other videos. I've got lots of things from cars to motorcycles to woodworking, all that stuff. So anyway, thanks for taking a watch and coming along with me, and catch you in the next one. Bye guys.